Thank you
So let
everyone
me,
for
please, sorry, Victor, let
voice.
me do a little presentation.
Oh yeah, my
Uh,
bad.
That's good. Sí. Buenas tardes, bienvenidos al Seminario Fronteras de Energía, organizado por el Instituto de Energías Renovables de la UNAM. En esta ocasión tengo el gusto de presentar al doctor Vitor Heitor Cardoso Cunha, que nos acompaña de la Universidad de Ciencia y Tecnología de Noruega. Antes de comenzar con la presentación, voy a realizar una breve semblanza académica del doctor Cunha en el idioma inglés. Dr. Victor Cunha received his bachelor and master's degree in mechanical engineering from the Pontificia Universidade Católica do Rio de Janeiro and his PhD in fluids engineering from the Norwegian University of Science and Technology, NTNU, where he investigated liquid vapor phase change and at submicron scales using a phase field version of the Navier-Stokes Korteweg equations. His research examined curvature-dependent thermodynamics, contact line dynamics in complex surfaces, absorption mechanisms, precursor film evolution, and surface energetics. He also develops high-order finite element and spectral numerical methods for simulating compressible interfaces and thin film dynamics. Nowadays, he's a postdoctoral researcher at Port Lab, NTNU. His scientific work centers on computational physics and interfacial thermodynamics, combining classical density functional theory for inhomogeneous fluids with phase field models for compressible multiphase flow. His current interests include interfacial thermodynamics, compressible flows in confinement, and absorption phenomena in systems dominated by strong density gradients and molecular scale interactions. Peter, thank you very much for accepting the invitation to participate with us. And now you may start, please. Thank you.
Thank you very much for the introduction, Filiberto. Thanks for inviting me. So I'm going to talk about dynamics of liquid vapor interfaces. This is my research is on interfaces in general, but I will retain the scope to liquid vapor interfaces and doing computational studies using phase field methods. So this work has been done in collaboration with Professor Maria Fernandino, Professor Øyvind Wilhelmsen, Professor Morten Hammer, Professor Carlos Dorão, and Julian Garcia Ran, an engineer. And it has been done at the Norwegian University of Science and Technology during my PhD and the postdoc. Oops. Okay, so first of all, just hello. I am Vitor Cunha. This is me. I come from Rio de Janeiro, Brazil. I did my master's there and bachelor's, like Filiberto was mentioning. And then I moved to Trondheim in 2021, looking into liquid vapor phase change at the nanoscale and looking in general, more general, at gradient structures. So I'm a postdoc at PorLab, which is a joint group between NTNU and the University of Oslo. And we're going to talk about fluid-fluid interfaces, more specifically liquid vapor interfaces. So liquid vapor interfaces, an interface is described is dividing something, right? So in this context, we have a liquid bulk and a vapor bulk, which is going to be characterized by some thermodynamic quantities. And the exchange of energy and matter between these two systems is going to take place at an interface, and this interface is very important. And there is a nice quote from Walter Britton. He won the Nobel Prize a long time ago about interfaces, which is where is just a surface where many of our most interesting and useful phenomena occur. And I couldn't agree more. If you see, for example, experiments of droplets condensing on a surface, and then you see that there is an interaction between the surface of the droplet and the substrate, the surface of this solid, and there will be a force balance associated to it. And this knowledge is very important for us to understand nature. For example, how plants breathe and how insects drink water on the harshest environments. And in this, if you look at the characteristics of these surfaces, they play a big role in the functioning. So we take this type of understanding is very important, because if you think about engineering, then the new iPhone 17 has a vapor chamber inside for cooling. And this vapor chamber, you have a microstructure surface and a net where evaporation and condensation takes place, helping us to cool down this cell phone. So as we go down to smaller scales, this kind of knowledge is very useful for us to improve our engineering designs and have a proper description of the system. The question that in my research is how to model all these interfacial phenomena as we go to small scales. So if we take a droplet as a model, this droplet will have a moving interface. It will exchange heat and mass. There will be the surrounding environment, which will play a role in the dynamics of the system. And this interface will have characteristics, like we have to evaluate the composition of the chemicals around the interface, the temperature of this interface, and if the interface is in contact with other surfaces, how do they interact with one another? So there are different modeling approaches. I'm not going to go into in each of these models, but these different approaches, they will require different assumptions about the interface functioning and the description of the interface. And there we have done a lot of interesting simulations and a lot of interesting studies at large scales using various methods. But there is a trend in the literature that they take this universal approach across all scales, and this is where I want to tackle how do these assumptions represent the interfacial scale. So as we go to smaller and smaller scales, the interface becomes surface forces become more dominant, and we have to account for the interfacial structure in all these phenomena. So this is the research line, my research line. So the idea is to use energetic descriptions to study interfacial energy and mass transfer phenomena to microscales. So we want to focus on dynamic settings and systems out of equilibrium, but of course we are assuming here local equilibrium conditions. And the idea is to have as fewer assumptions for the interface as possible. And we're going to use a free energy description. This is basically, we have a free energy that describes the energetics of the system, and we use equations of state and thermodynamic modeling for continuing the modeling process. And this, coupled with the phase field methods, we get to represent the state of the system through order parameters, and that gives us a set of evolution equations for an order parameter. For example, if we have a liquid droplet and we want to model this using a phase field method, we will be this droplet of liquid surrounded by vapor is going to be represented by an order parameter that will capture this smooth transition in contrast to a sharp interface description. So this characterizes this bulk of work as a diffuse interface method. So with this free energy description, what does it mean? I will start the description of the problem by defining a grain potential functional. And this grain potential functional will have a contribution of a free energy contribution and interactions between an external subjected to external forcings and conservation of mass, for example, which is where this chemical potential come. And the process, we have equations of state that helps us closure these models, and the extremization of this grain potential will yield the Euler-Lagrange equation that will describe thermodynamic equilibrium. So we take this. There are two different ways to address this problem, two different descriptions of the problem. One is towards the density functional theory, which is more into the atomistic scale and particle scale. And you have a truncation of this model, which is density gradient theory, where it makes it easier for us to couple with continuum mechanics and the Navier-Stokes equations, for example. So I'm going to focus on the results I have for density gradient theory. And someone is asking to be admitted. And yeah, we will have a free energy description here. And with the density gradient theory, this is how the Helmholtz free energy would look like. We'll have a bulk contribution and a gradient term that is weighted by a capillary coefficient. This is something that we need to model, and plus boundary effects on the free energy of the system. So we use van der Waals equation of state here. That's why I mentioned the qualitative results, nature of my results here. And this gives us some closure relations for the free energy density. And we will have a Lagrangian that will describe the system. And using the translation invariance of this ground potential functional, we get to describe this, to determine this conserved momentum flux tensor that will encode capillary effects in interfacial mass transfer processes. And this, combined with the Navier-Stokes equations, will give the Navier-Stokes-Korteweg equation. This is our set of equations of motion. And in this model, we have viscosity, external forcing, inertia, and capillarity, of course, together with boundary conditions and the closure relations for everything. I'm not going to go deep into the equations, but of course, feel free to ask about it. So with this model, the goal of this presentation, I'm going to talk about how the formation influences evaporation and condensation at submicron scales, the droplet motion on surfaces with non-uniform wettability, and the dynamics of wetting and vapor adsorption. So bear in mind that these works are assuming submicron scales, less than a micron. So we're going towards a nanometer as a length scale. But of course, this as a continuum model, this will be qualitative analysis. So if we start thinking about the impact of the formation on evaporation and condensation, we have our description of the interface. We have our model, which describes this interface as a diffuse interface. And now this droplet is deforming. So the interface is deforming, and then it can have some shapes, some more elaborated shapes. And at small scales, there is a geometric relation between mass flux and curvature. You probably heard about the Tolman length and how the curvature influences surface tension. There is the Kelvin effect, which is when the curvature also influences the local saturation conditions, and thus affecting the mass fluxes during evaporation or condensation, for example. So for this first case study, I defined this canonical case, which is an elliptical droplet surrounded by its own vapor. This is a van der Waals fluid, so a fluid system modeled by the van der Waals equation of state. And this is a two-dimensional system. So we are going to look into how does the evolution of this droplet, this initially deformed droplet, how does the formation interplace with the evaporation process? So the droplet is going to be evaporating due to a temperature difference, and because we're going to initialize the simulations with a deformed elliptical shape, the surface tension is going to try to minimize the surface area, and then it will induce an oscillation. And because this is a viscous fluid, so there will be a viscous dampening process, and thus the droplets will tend towards a cylindrical shape, which is in these two-dimensional simulations. These are cylinders, actually. So if we track this horizontal radius that I set in the figure, this Rx, we see that there's an initial oscillation, and during the evaporation process, the radius should decay. And we see that the oscillation does not affect the droplet lifetime in this canonical case. The various initial conditions will affect the amplitude of the oscillation, but it seems that the global evaporation process, this case, it's not affected by this setup. But there is in the literature cases where you study droplets subjected to external forces, for example, acoustic force, and there will be a everlasting oscillation process, and thus the evaporation is affected by this deformation process. So we see that if we integrate the mass transit, the mass flux along the interface in this sort of functional, we see that there's not significant impact on the droplet lifetime during deformation. But this is not the interesting part that we want to look at. We want to look at the interface while it's deformed during this process. So let's look into the local aspects of this process. So if we plot the pressure, the total pressure of the system, which is the thermodynamic pressure plus the gradient terms, we see that as expected, capillarity will yield a higher pressure in the highly curved regions, and this is the driving force of the oscillation, of course. What we see also is that the temperature field is lower in the regions of higher curvature, and there is also lower pressure in the vapor near the curved regions. And this is an indicative of how curvature can affect the local saturation conditions. So if we imagine ourselves walking along the arc of this interface, the top arc here on this sketch, and we measure the interfacial mass flux and also measure the curvature of the droplet of this interface, we see that this figure on the right here, which is we have the mass flux along the interface plotted together with the curvature. As we see here, this model allows us to capture this relation between mass flux and curvature without assuming anything regarding the interface characteristics. We're not defining a specific directly a model for the interfacial mass transfer, some dependence or some jump conditions at the interface. We're not assuming that, which is the interesting thing about this modeling. If we capture the pressure and the temperature at the interface, and also capture the pressure in the vapor near the interface, and we compare this with the expected saturation temperature with that given pressure, we see that in the model we have a reduction of temperature in regions of higher mass flux, and this is the indicative of evaporative cooling. There's a cooling associated with the evaporation process. So this is another indicative of the Kelvin effect, which is it is something known that the Navier-Stokes-Korteweg model and this type of gradient description of capillarity is capable of capturing. And this is just the dynamics of the system is also showing this effect. And you can look at this Kelvin effect from an energetic an energy transfer process. For example, as there is evaporation, higher evaporation fluxes in regions of higher curvature, that means that there is more fluid expanding, and thus there is a higher consumption of this energy, which is manifested in this pressure energy flux, which is basically all the components in our energy conservation equation. And because of this cooling effect, there will also be an associated diffusion flux along the interface, the tangential direction of the interface. So these results are presented in a paper that in the International Journal of Multiphase Flows. The goal of this work is to try to benchmark if the Navier-Stokes model is capable of capturing these behaviors in a qualitative manner without having many assumptions regarding the interface characteristics, and focusing this research both towards these small scales where we define the system, the characteristic lengths are of submicron scales of 100 nanometers in this scale here. So we follow this work, and now we start to include substrates. The goal now is to include substrates and substrates with varying wettability profiles. So basically, imagine if you have, for example, a surface whose chemical coating is non-uniform, or it might happen by accident, or you might do this on purpose. There are applications for that. In microfluidics, for example, there is research on people stretching DNA strains by having the droplet evaporating on a wettability gradient surface, and then you have this aligned DNA on the surface. So this is a very interesting application, and what is happening here is the wettability gradient. Imagine a droplet will experience different contact angles across its contact line. So this will, because there is a different surface energy that this contact line is experiencing, the contact angle that manifests from this force balance will be different, and thus resulting in curvature differences on the at the interface of this the liquid vapor interface. So we will see a region of higher pressure and a lower pressure inside the droplet, creating a difference that will propel the droplet. So this will be the self-propulsion of this droplet, how it comes to be. So we are interested in that because in the group we were looking into some microfluidic experiments, and there seems to be several assumptions regarding this modeling this process, and this is again is fine at the larger scales, because then you can assume that the droplet is rather spherical. But as you go to smaller and smaller scales, the droplet shape influences a lot. It will influence a lot the energetics of the system, and then we want to see if we're able to capture this process without having all these assumptions. So we rely on the minimization of the grand potential function, that the Euler-Lagrange equations there will be an associated Euler-Lagrange equation at the surface, and this will give us a way to describe the surface energy, so that we can have this capillarity description in terms of surface energy process. So for this bulk of work, we define this study case here, which is a droplet, a liquid droplet resting on a surface, and then we model the surface energy, this substrate energy. We model the surface energy using a surface energy difference, and we have a model for this. This is a known model for phase field methods, where you define the surface energy in terms of these interpolating polynomials. And what we do here is we define this interpolating polynomial as a function of space as well. So in this case, we are looking into self-propulsion, and we're going to look into how condensation and evaporation affect this self-propulsion process. So when we start massaging the boundary condition, we get this nonlinear equation, and we basically impose a surface energy profile, like in this case will be a linear surface energy profile, and then we look into the self-propulsion process. So when we start the simulations, all the simulations are started, they begin with the same initial conditions, and then we let 5 time units pass, so that we trigger the phase transition, and we're gonna trigger this by a temperature difference of 0.01 in reduced units. We are here in the simulations, I forgot to mention, we're close to the critical temperature here, so that's the qualitative study that we have. And then we have this triggering of the evaporation condensation that will affect the surface energy of the substrate, because of the dependence of the surface energy on the density, and that's hence the nonlinearity of the boundary condition. So if we see that the condensation increases the droplet volume and thus the wetted diameter of this droplet, whereas evaporation will reduce the volume. And this plays a big role. And this also plays a role in the spreading process. And since we have a wettability gradient, the regions of high surface energy will be hydrophilic regions. They will like to be wetted, and the regions of low surface energy will be the hydrophobic regions. This wettability gradient is coming from low to high, so the droplet's going to move to right, and the contact angle at the front of the droplet is going to be different from that of the back of the droplet. Just to a reminder, this is a 2-dimensional simulation, so that's why but this analysis should be taken into along the contact perimeter, the contact line. So this change in this difference in contact angle, the front and the back, this is just the how you quantify the driving force in this process and in this system. So there are some expressions from literature that are derived from dimensional analysis of the system. So we get a driving force that will be influenced by the wetted diameter and the cosine of this contact angle, and we'll also have a resisting force coming from viscosity. So we want to measure that and how does phase change affect this force balance. So we see that in condensation, as we expected, because we're increasing the wetted area of this droplet, the driving force will increase as well. And interesting enough, there is some oscillation, which I'm going to talk later. The overall behavior of the system is that the driving force is increasing with condensation and is rather oscillating and plateauing for evaporation. We see here that the biggest dependent of the driving force is the wetted diameter, as we expected from the equations, right? And in this study, we are assuming the early stages. We are looking at the early stages of this transient simulation. So the driving force is bigger than the viscous resistance. So we can estimate some velocity scale so that we know that we are in this regime. And if we measure the migration velocity, which is basically the horizontal velocity of the center of mass, we see that there is a linear trend. The evaporation begins hindered, but it increases slightly. But there is more work that needs to be done on this characterization. And you can see also that the viscous resistance, the viscous force increases with condensation as well. And then with evaporation, that increases quite a lot. And you can see why the driving force is not increasing as much as in the condensation. Condensation speeds up the viscous resistance by having a larger wetted diameter, and yes, this is the overall of this process. We can also look at the interfacial mass transfer process, which is what we are interested in, and we again find similar trends. The trends we found in the previous work, where the the curvature of the liquid vapor interface is going to be affecting the mass fluxes along these regions. So this is there's a lot to unpack in this graphs here. So on the left, you have mass flux as a function of along the interface arc, and we also have the temperature along the interface arc, and you'll see that the regions of higher evaporation will yield a lower temperature due to evaporative cooling, and condensation will also increase the temperature due to this capillary condensation. The temperature is increasing due to condensation. So what we see here, I don't think I should read this part. Let's just summarize this. Condensation in these results are favored in hydrophilic regions, and evaporation are favored in hydrophobic regions. This is known in the literature. We see this trend that the higher curvature regions will hinder the condensation process, and the evaporation is favored in these same regions. So you see again the dependence of curvature and mass fluxes along the submicron scales. There is also very interesting internal dynamics happening in these systems. So, for example, because we're not imposing a contact angle law or a dependence of the contact angle on the substrate temperature, it's rather coming from the system trying to equilibrate the density at local equilibrium for that specific condition. We see that as we go along the simulation begins, and we have we trigger evaporation by increasing the temperature of the substrate, and we trigger condensation by reducing the temperature of the surface. So this will manifest in evaporation. The increase in temperature will result in higher contact angles, or contact angles, more hydrophobic contact angles, and regions of, and when we trigger condensation, we have more hydrophilic contact angles. And because in condensation, the droplet is increasing its volume, there will be this change in both cases, actually. The change in contact angle will yield a capillary wave. And this capillary wave will result in periodic shifts in the pressure distribution. This is more pronounced in the evaporation case because the droplet is shrinking, whereas the condensing droplet is increasing its volume, and thus the dampening is faster. But this is something very interesting that we found, and is coupled with a lot of internal circulation, which is, again, linked to an interfacial mass transfer process. So this is a very rich a type of simulation setting that we found, and we've seen some interesting works, simulation works in the group looking into that, but meaning that this is a very interesting type of simulation that's unfolding some of interesting internal dynamics of these systems. This work has been summarized and in this paper again, and we have some nice remarks that condensation enhances the force driving the self-propelled motion. So condensation could be used in applications. Both condensation and evaporation could be used in applications where you want to do the self-propulsion processes. But again, this is a qualitative study, so there is the need to quantify these works, which I'm going to mention later in the end of this presentation. So we're going to move now to a last topic that we're gonna talk about this in terms of applications of this methodology, and it's on nanoscale wetting. So the canonical case for studying this systems is by having a thin film, and this is basically the backbone of coating technology. So this is quite useful and interesting for us. And again, we're looking at submicron scales, and so this bulk of work will have a reference scale of 50 nanometers, where we're gonna define our dimensionless numbers and the reduced system in reduced units. And we're gonna look into how evaporation, condensation influences the thin film stability and dynamics. But in this case, we are looking into a nanothick film, so of 10 nanometers thick. And this is, again, a van der Waals fluid. But in this case, if we're simulating this, we have a influence of the solids on the fluid molecules, on the fluid particles, and this influence is non-local. So basically, there will be an interaction, but a potential energy that will vary with space. And this is the long-range forces here, or the joint pressure, if you would like to say it. And there are several methods to simulate these processes. For example, molecular dynamic simulation will give you very nice and quantitative results. And you can conduct equilibrium analysis on these processes. But we are interested in transient studies. So we want to use a different method. And again, to use molecular dynamic simulations, we will get very good results, but at the expense of a lot of computational power. Nanoscale systems are still at the order of fractions of moles. So it is a lot of molecules, and it becomes easily impractical. So we want to be in between these scales here. Phase field methods is like I mentioned before. It's an energetic description of the system, so there is some advantage in that. But there is something. The way phase field methods describe the surface energetics is by taking the boundary of the system and analyzing the entropy production of this boundary. So you get all the dynamics of the system of this boundary comes from analyzing the boundary as its own entity. It does not extend to bulk. Of course, it will manifest as a boundary condition, and it does influences as our previous work, but it does not manifest to the bulk in the sense of representing adsorbed films, for example. So we are looking in this bulk of work, we want to look into how the solid fluid interactions, such as attraction and repulsion, would alter adsorption, thin film stability, and phase change, evaporation and condensation of these thin films, and looking again into the dynamics of the system. So for this case, we will recall that we have a Lagrangian, and we're going to use this to include a finite length, a truncated potential, some sort of potential inspired by density functional theory. But we truncate the potential at y equals 0 because we don't want to generate infinite momentum. It's just a practical choice. This potential can be anything. We chose to have this parameterized equation just for this because it was better for the simulations. They were more stable and was very easy for us to test with different types of qualitative interactions between the solid and the fluid. So we will have repulsion and attraction, and we are going to be modeling it by the parameters of this film, of this potential. So we will get an interaction region which we'll be interested in. And this is where we are going to look at to focus our analysis on. So we will have a complete wetting process, and we are going to look into pure vapor systems and thin films, and looking into the evaporation and condensation of this process. And this system is going to be subjected to partial confinements as well. It is there is ongoing process on the effect of confinement on these systems, but this is for another talk. So for pure vapor systems, what we expect is that as the simulation runs, we will have a adsorbed film, the formation of this adsorbed film, and this is depending on the structure of this solid fluid interaction potential. You will have different structure of this adsorbed film, and if we just draw this line at the center of the vertical line at the center of the domain, we can do some sort of post-processing studies, and we can track the maximum value of the density field, which is it stabilizes at some point very quickly, actually. And the density at the wall measured at y equals 0 also stabilizes in a similar way. And you see that the shape of the interaction will influence these values, these values where the system reaches some sort of quasi-equilibrium condition. So if we take the last time step where we have some equilibrium state, we get to plot the profiles that we get for the density field and the pressure field. We see that this methodology that we are using is matching the results obtained with density gradient theory. Of course, you would expect in a realistic setting, we expect some sort of layering happening here. But remember, we're using gradients, density gradients to represent interfacial energy, and the layering is something that requires some sort of atomistic information that we need to inject into the system. So, for example, density functional theory would give us some sort of oscillatory layering, but density gradient, this should not be expected in the simulations. What we get as well, if we measure the total pressure of the systems, we get an analog to a disjoining pressure, but the disjoining pressure is a type of pressure that is it's subjected to some conditions, and this is a general pressure that we measure in the simulations, and it just has this qualitative the similarity on the system with the disjoining pressures. So when you have these adsorbed layers formed, you will expect some energy budget that would need to be met. So we can track that using just measuring the enthalpy of the system, an enthalpy defined with consideration of the gradient terms, which is obtaining. You can define that using this density gradient theory. So what we see here is that these are high pressure layers, and there is consumption of energy in their formation. So it's kind of like a condensation process. Yeah. So if we look now into the case with thin films, this is where things get a bit interesting. Thin films, and they are evaporating and condensing. So when we have just a thin film and we see how does the system respond to this external forcing, this system will re-stabilize, and then we'll just settle back when we're not triggering a phase change, and then it will just be quite stationary. But when we trigger evaporation and condensation, you see that this interaction potential will affect the mass fluxes. So if we trigger a condensation, condensation will increase the thickness of the film, and this increase is going to decrease. It's going to be less pronounced because of the thermal resistance during the process. So there will be, these are the profiles. You get the blue curves here. So I also plotted the cases of condensation and evaporation without the potential, which are the dashed lines. So you see that for condensation, there is not a big of a difference in the thickness of the film, but there is some difference in how the mass fluxes are behaving in the at longer times. Of course, these are very small differences, but the qualitative behavior is, you see that the condensation will keep on happening, albeit very slowly, without the potential. And with the potential on, you would expect this film to not to need this mass flux to reduce in magnitude. With evaporation, the film should evaporate completely, and this is what we expect. But with the potential, we will expect to have some sort of resistance, and this is what we get. We get these non-adsorbed layers because solid fluid interactions will be holding the fluid onto the surface, and these curves, they change a lot depending on the shape of the interaction, meaning that how the attraction and the repulsion will be modeled, will be included. What kind of balance between attraction and repulsion is this potential representing? We also see that there is again the evaporation condensation. You will have with the potential, you have these joining like pressure profiles. And this is a very interesting result because it's related to, allows us to look into, for example, the dynamics of precursor films, which is something that we are looking at. How do these models are able to capture precursor films? So this work has been summarized in this last paper. And this is a very interesting work. There's a lot of ongoing research on this topic now. So I hope to get to give you some other feedbacks in the near future. And to conclude this presentation, so we want to look at this group wants to look at the nanoscale fluid dynamics. We look into how surfaces interact with droplets, and how do these affect interfacial mass transfer processes. We are motivated by the ongoing miniaturization of electronic devices, and how we need to actually improve the modeling of this at these small scales, having a representation with as less assumptions as possible. But there is a lot to improve here. These are, again, qualitative results. We are using a van der Waals equation of states, so there are more advanced equation of states to represent the systems. We are simulating, all the simulations have been done using considering a single component system. So we basically have a liquid on its own vapor. So there is, you have to consider fluid mixtures as well. So there is also work on that direction. Something I've been working myself quite a lot is to include fluctuating hydrodynamics into the system, because as you go to small scale, you need to incorporate thermal noise. And there is some very interesting research using the Navier-Stokes-Korteweg model with fluctuating hydrodynamics, basically the fluctuation dissipation theorem. for cavitation processes. So, and there's a lot of work from people from Italy, and we are also this system, as all the simulations regarding wetting have been assuming a instantaneous equilibration of this contact angle onto the force balance. And this is basically a static contact angle model, and we are able to vary this by having varying surface energy. But there is some sort of time scale of the contact angle that it needs to be included, and this is where dynamic contact angle models enter into play. The nice thing about these phase field methods, which are thermodynamically consistent, like based on free energy descriptions, is that if we have a proper, for example, description of the entropy production at the surface, we're able to derive some models which are, for example, the generalized Navier sleep model. And this is a model that is a model for dynamic contact angles that is not assuming a lot apart from this some parameters, but it's not assuming a rule for how the contact angle should move. And this is quite convenient for phase field methods, because then you integrate everything within the same methodology. So thank you very much, guys. This has been a very interesting experience and opportunity. So muchas gracias. And that's it.
Thank you, Vitor, for your interesting presentation. So we start with the question session, question time. You may raise your hand, ask directly to the speaker here, write in the chat, or on YouTube, you can write in the chat of the video, and we can ask Vitor. Professor Mariano, go ahead.
Thank you, Filiberto, and thank you, Vitor, Heitor. I would like to speak in Brazilian, but I don't dare. Anyway, I have a couple of questions. One has to do with the outline that you gave in the last transparency, namely the effect of the equation of state. You chose, of course, the easiest or the most fundamental equation of state, including a phase change, a liquid vapor phase change. What would you expect on the use of the more advanced equations of state? What effect would you expect on the results that you actually have now?
I would expect a refining of the magnitude of the interfacial fluxes happening, some sort of a reflection on the mass transfer process. That's what I would expect, which would also be how for example, increasing a change, including different components, a fluid mixture, how that affects
that I find more interesting. I think. Yeah. I think if I may, the equation of state will also give you, of course, will give you a refinement, but I don't think you would be able to detect anything out of that. The effect should be too small, probably.
I see.
Probably. That's just a guess. I mean, I haven't done any calculation, but I would suspect that the effect would be small. The other thing I was curious about, and that's just curiosity, when you set up the hydrodynamic equations,
yes,
I missed one of the symbols over there, which was a pi, and I don't know what that refers to.
Oh yeah, okay. I guess maybe if I can come back there. There is this system. I haven't mentioned the numerical aspects of solving this problem, which is its own challenge. So if you expand, let me just go back to the model here.
That's it.
You expand when you take this Lagrangian into this expression here. You get a second order tensor, a second order.
That's a pi. Okay.
On the density field, and by taking the divergence of it, you get a third order system, and this limits what kind of numerical methods we use. We in this work, I focus on the finite element methods, and we chose to reduce the order of the system by having another term. If I don't know if that's what you're asking. but we reduce the order of the system so that we can use C1 continuous elements, basis functions in our finite element method. But I hope that's the term that you mentioned. I don't remember.
Yeah. It's the pi that appears in the energy equation, which I couldn't figure out what it was. That's
pi.
it. Yeah, the pi.
Yes, that pi is it's called the interstitial working flux.
Okay, yeah.
That
I hadn't seen before.
This is a bit different, actually. This is not what I was talking. This model.
Yeah, go ahead, because I have another question now.
This model has been derived. It's been quite old. So it was a student of Van der Waals, Korteweg. He tried to describe capillarity in terms of density gradients. And then there was in the 70s, some people realized that the model was thermodynamically consistent, meaning that the entropy of production was lower than zero, I think. And without this term, that's the term that makes the model thermodynamically consistent.
Okay.
Then the system would not work. So this is the model. This is the term pi.
Now the final one. Sorry, Filiberto, but
no worries.
Go ahead.
And now that you have the equations, that I have the Navier-Stokes-Korteweg equations, when you do fluctuating hydrodynamics, what do you add? Do you add the fluctuating term to the momentum and to the energy equation, and then generalize the fluctuation dissipation theorems?
So in technically, the fluctuation dissipation theorem would yield these fluctuation terms on the tensors, right? And this will show up in the momentum equations and in the energy equations. But when you work on the energy equations, you're able to simplify these terms. So there will be the heat flux will have these fluctuating term.
Yeah.
The momentum equations you'll be able to work it out by massaging the equations and finding the something that you can simplify. But yes, you include that through the tensors of this vectors and tensors of the tensors of the system.
Okay. Well, thank you, Vitor. I hope I wasn't too intruding.
Okay. No, absolutely not. It was very nice.
All right.
Okay, thank you. Other questions?
I have a question, although
Go ahead, Professor Martin.
I don't know how I can put my hand.
It's okay.
I don't know how
you may ask. Yeah.
I mean the hand that Mariano put. Yeah. Thank you. Well, this is to me very interesting, and I don't know how much I believe you. And the reason is because everything I know of wetting has to do with, it's very important, the intermolecular forces. And so you have forgotten all of that. And if you think of water, for example, and you think about the magnetic, so the dipole interaction of the molecules among themselves and with the structure, the surface. This of course change a lot. So I mean, I like what you did. It's very interesting, but to me very surprising. In fact, I don't know if I believe you. So the point and the reason that I'm not being aggressive, I'm just saying I am impressed that you can do this without taking into account the structure of the drops and the substrate. So one question I have: how low can you go? So it's like, I have worked in the past with molecular hydrodynamics.
Yes.
But to do that, you have to have the information of the structure, the molecular structure, to do that.
Yes.
Here you forget all about that, and so you just do energy and force balance equation, which is very nice.
Yeah.
But at what level, the theory breaks down?
Oh yeah, this is a very nice question, actually. There is some reports on people using classical thermodynamics up to 2 nanometers. There's Professor Janet Elliott from Canada, from the University of Alberta. She has done some studies on that. And of course, she can measure the Kelvin effect to a certain accuracy at very small scales. And she mentioned that this assumption gives you a good estimations. This modeling approach where you don't consider the exact, still have a coarse grain description of the fluid. You still have some prediction capabilities at very small scales, but of course, as you start, like when you start going to 1,000 length scale where you have 1,000 molecules packed. Let's imagine the diameter of a droplet is of 1,000 molecules. Then how it is, definitely you need some molecular information. And in this case here, this is a gradient description where the interface, where the covalent forces between the molecules will have this shift because of the difference in the setting. This is modeled by this term here, this gradient of the density square, and this influence parameter, this kappa here, is where you define this kappa in terms of the molecular structure. Actually, you can define that. This is how you connect density gradient theory with, for example, density functional theory. In fact, this whole methodology, you're able to, instead of using density gradient theory, you're able to use density functional theory. And there you can have, for example,
I know.
Yeah. So this is how you would improve this. But I agree with you. We need to be very skeptical. That's why I kept repeating that these are qualitative results, because this is not,
Yes.
we're now at the nanoscale. I'm claiming to be at the nanoscale. So it's at the nanoscale, there are things which we need to consider, and the structure of these interfaces that comes from the atomic arrangement, molecular arrangement, needs to be considered. The smaller we go, definitely. This is just a coarse grain approximation, so we can get the qualitative behavior of the system. That I hope that has answered a bit of the question.
No. I think it's very nice, because doing the other, I mean, you mentioned at some point that doing, for example, molecular dynamics is very expensive, and I totally agree. I mean, this is a way of going around and have some interesting results. Another thing that you are missing is that you are looking into one drop.
Yeah,
okay,
no,
really
absolutely.
You are not okay, and this is going to change. I mean, the entropy is modified if you take the interaction between the droplets, etc.
No, absolutely.
So finally, I tell you that I did like your talk very much, and I have been to Brazil many times in the past, in particular to Ribeirão Preto.
Okay, I haven't been there.
Ribeirão Preto, yeah.
Yes,
okay.
I heard about it.
I have been in Rio de Janeiro, but also
Nice.
in Ribeirão Preto. Well, thank you very much.
Thank you.
Thank you, Professor Marcelo. Professor Eduardo Ramos, go ahead.
Thank you very much for a very nice talk. I was just, I wanted to ask you if you can comment on what happens if you have not only vapor, but also an inert gas, like for instance, air. Because in our experience, when we introduced this third component in the picture, then things are completely different. And also, if the body, whatever, the drop is moving with respect to the air, then it complicates the picture enormously. If you can comment on this, I would appreciate it.
Yes, absolutely. I've done some work on like extending this model to multi-component system. There is a lot of people trying to do that, because as you mentioned, a single simple droplet surrounded by its own vapor is a rather canonical case. And as you have like an inert gas, for example, you have to the whole interfacial mass transfer process is going to be modulated by a partial pressure, and this will change completely the dynamics of the system. Probably this will hinder this influence of the mass transfer onto of the curvature on the mass transfer, or the local mass transfer process. Definitely. The thing is, the characterization of the interface will be it will be interesting to see how the interface is interacting with this inert gas, or not inert gas, or with some sort of other components. How will that affect the temperature of the interface, the partial pressures, and then in a dynamical setting, in a fully dynamical setting, how would that affect the system? There are some numerical simulations. I've a couple of friends of mine have been working on the same problem at the larger scale with a multi-component system, but using a different methodology. And they found that when you have multiple components, the mass fraction will also be distributed along the interface, and this is a very interesting thing. There will be pressure differences induced by this curvature, the influence of the curvature of the shape of the droplet. And when, for example, you have a droplet breaking and droplet collapse, and they break and they get together again, and in a dynamical setting, this influences the overall global energy transfer. So in a decaying turbulent setting, for example, a cluster of droplets moving will the evaporation condensation it will influence the energy decay. The local energy of the interfaces will affect the energy, and there's nice research on this line published. So I would imagine my results to be rather different because this is a simple system, but there will be there are other phenomena that I think are interesting that are happening at the interface as well in these settings.
Okay, well, thank you very much. Please, would you send Filiberto the reference you mentioned about this going to very small scales, nanoscales, the person in the University of Alberta in Canada?
Yes, absolutely. I can send
because we have also interest in this kind of problems.
Yes.
Thank you very much for your talk and for your answers.
Absolutely. Thank you.
Thank you. We have time for one more question.
Well, if there is time, I have another question.
Sure.
Go ahead,
Marcelo.
Professor.
I'm sorry.
Yeah,
Let me put I don't know how to put my hand, you know, how to raise the hand with this software. But anyway, so, you know, what happens if you have charge, electrical charge?
That's an interesting
Have
question.
you considered that?
I haven't considered that. It's a bit out of my scope. I have never worked with electric charges. I can imagine that you would be able to include that into the free energy, into the ground potential functional. So you would have a contribution to the electric charge. But I don't know exactly how would that influence these results. I imagine that within this framework, it could be possible to simulate the systems, but I don't have an intuition to comment on.
The potential that you're putting in, it would have to be perhaps more than Lennard-Jones, because because it's a long range interaction. It goes much far away
on the interactions. Yes.
Anyway.
Yes. No. Absolutely.
It will be interesting.
Yeah. I think there is.
Thank you very much.
Something like that. Yeah. If I remember correctly, while I was writing my thesis, I think I stumbled on a few papers looking into how the substrate charge. I can tell for sure. I should shut up now. I can tell for sure if I remember this correctly. Yeah.
Yes. Well, as you were saying, you have the approach of density functional function, then it's no problem. You can you just can put in everything you need.
Yeah,
You just
yeah.
change the potentials, and you just can
Yes,
do it that way.
anyways.
It's hard, and you will have to make strong assumptions about the intermolecular forces. But
Yeah,
no, but I think your approach is simpler in a way. I mean, like it's less demanding computationally.
yeah,
So I was curious if you could apply this to
yeah.
charged fluids.
There is
Okay,
a.
thank you very much.
You're welcome. Just one last comment. The density gradient theory is a simplified theory for how this inhomogeneous fluid systems are structured. But they are able, for example, to capture with a lot of accuracy the surface tension of various fluids at various temperatures, including surface tension dependency. And this is the interesting thing about it. With this rough description of the system, we're still able to capture some quantities which are quite useful. For example, if you have a good representation of surface tension, then capillarity can be modeled here. And of course, not in this setting, but density gradient theory can be used to give you actually quantitative results of surface tension values. But like you said, absolutely, if you need the structure of the interface, which as lower the temperatures we go, if we want to look into influence of microstructures, surfaces, if you have point tensions because the surface that is being wetted has conical pyramids or structures like that, then it is a different system. Yeah.
Yeah, and also it will be limited by the size of the rock. I mean,
yeah.
Perhaps this approach is broken.
Yeah. Perhaps when we reach that point, then we go to molecular dynamics.
Yes. Okay, thank you very much.
Thank you.
Well, thank you very much. Thank you very much, Vitor, for your very interesting presentation.
My
and thank you all
pleasure.
for your attention. Bye-bye.
Bye-bye.